Hello students, welcome to Time classes. This is the second session of the chapter Light, Reflection of Light. Before going further in the class, let us have a quick recap of whatever we have discussed in the previous class. We have discussed that light is a form of energy which gives us the sensation of vision. There are major phenomena out of which two are mainly important for us to see the world. One is the reflection, another is the refraction. So currently we are discussing about the reflection of light. Reflection is nothing but bouncing of the incident light on an object. That's what we have defined earlier. Okay. Then we also discussed the laws of reflection. What are the laws of reflection? Just try to recollect. Open your notes and then try to recollect. See what you have noted down in the previous class. The laws of reflection are nothing but angle of incidence is equal to angle of reflection, the incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. These two laws constitute the laws of reflection. Then we have seen what is a mirror, a plane mirror and a spherical mirrors also. A plane mirror is the one which is a surface is plane, it is smooth, highly polished, a glass piece. Okay, silver coated on one side, and so does the 100%, nearly 100% reflection on the other side. Now, if it is a spherical surface, the surface itself is not plane. So, whatever the reflection laws of reflection are there, they are valid both on plane surface as well as spherical surface also. The difference lies in that in the case of plane mirror, we do have regular reflection, whereas in the case of a spherical mirror or any other surface, we do have irregular reflection. We also have defined the differences between regular reflection and irregular reflection. In the case of regular reflection, an incident parallel beam of light will be reflected as a parallel beam of light. Whereas in the case of an irregular reflection, an incident parallel beam of light will not be reflected as a parallel beam of light. This was the major difference what we have noted, right? Next, we discussed about the properties of the images formed by plane mirrors. In the case of a plane mirrors, if you see the characteristics of the images formed by plane mirrors, the first one is the object distance and image distance both are equal. When we measure the distances, we take the plane mirror as the reference. The size of the image is equal to the size of the object. Okay. The image is virtual, it is erect as well as laterally inverted. Okay. These are all the properties of the images formed by plane mirrors. Next, we also discussed about spherical mirrors also. There are certain points which are important, which constitute the terms related to spherical mirrors. Let us have a quick recap of those points. The geometric center of a spherical mirror is called the pole of the mirror. Okay. The center of the sphere from which the mirror was cut off is known as center of curvature. The line joining the center of curvature and the pole of the mirror, an infinite line, this is called principal axis. The distance between the center of curvature and any point on the spherical mirror will be equal to the radius of curvature. If I take a straight parallel beam parallel to the principal axis, which is nothing but the straight line passing through the center of curvature and the pole of the mirror. Okay, if I take an incident parallel beam parallel to the principal axis, after reflection, it will pass through one particular point on the principal axis in the case of a concave mirror, or else it will appear to diverge from a single point on the principal axis in the case of a convex mirror. That particular point is called the principal focus, and the distance between the pole and the focus is known as the focal length. We also have derived what is the relation between the radius of curvature and the principal focus. Okay, just try to recall it. We have seen that radius of curvature r is equal to twice the focal length f. Okay, then we have seen some rules and regulations to be followed, okay, in construction of ray diagrams for spherical mirrors. Rule number 1 is, if a beam of light or if a ray of light parallel to the principal axis incidence on a concave mirror, after reflection the light ray will pass through the principal focus. Okay. On the other hand, if it is a convex mirror, if a light ray which is parallel to the principal axis is incident on the convex mirror, it will appear to diverge from the principal focus. That is the first one. Second one, what we discussed is that if a light ray is passing through the principal focus of a concave mirror and incidence on the mirror, after reflection, this will pass parallel to the principal axis. Same way, for a convex mirror, if a incident light ray is directed towards the principal focus, after reflection, it will pass parallel to the principal axis. The next point what we discussed is that if a light ray is passing through the center of curvature of a spherical mirror, is either incident on the concave mirror or on the convex mirror. That means if it is directed towards the center of curvature in the case of a convex mirror, then the light rays will retrace their path, because the light rays in this case will be passing along the normal to the point of incidence. Normal to the mirror at the point of incidence. So when the light ray is incident normal, obviously the angle of incidence is 0, so the angle of reflection is also 0, so the light ray will retrace. Clear? And one more point also we discussed, that if a light ray is incident at the pole of the mirror, either in the case of a convex mirror or a concave mirror, it will undergo reflection such that the angle of incidence is equal to the angle of reflection. So these are all the points what we discussed in the previous class. Okay, just to have a quick recap of the things. Now let us proceed further to know the nature of the images formed in the case of a concave mirror and a convex mirror. Let us proceed first with the concave mirror. Okay, I am taking a concave mirror here. Now, to know the position of the image of an object placed in front of a concave mirror, we will use the rules what we have discussed in the previous class and what we have explained just now in the recap of the first class. We will use those rules to know or to construct the ray diagrams in order to know the position of the image of an object which is placed in front of either a concave mirror or a convex mirror. But let us now begin with the concave mirror. So here I am taking a pole. This is the pole of the mirror, concave mirror. Okay, I am taking a center of curvature C. I will take a line. This is the principal axis. Now, if the object is placed at infinite distance, So what will happen? Light rays will come from the infinite distance like that. They are incident on the mirror, and after reflection, following the rules what we have discussed, they will pass through the point on the principal axis, single point, that is nothing but principal focus. Okay. So where is the object? At infinite distance. The light rays after reflection here are converging at the point F. Okay. Because these light rays are converging at the point F, whatever the nature of the image we get over here, it is a real image. What do you mean by real image? A real image is the one which can be caught on a screen. So now the light rays after reflection are converging at the focus. So if you place a screen at the point F, then we'll be able to see the image of the object placed at infinite distance from the concave mirror at the focus. Okay. Second point is it is very much highly diminished. Okay. Because we are getting the image on the screen, we'll call it as a real image, and this image will be inverted with respect to the object. If I am taking the tree, this tree will be appearing upside down. That means the roots or the bottom of the tree will be appearing at the top portion of the image, and the top portion of the tree will be appearing at the bottom portion of the image. That is what we mean by telling it as inverted. Okay. So the image is inverted, it is real, okay, and highly diminished. We are using the word diminished because it is very, very small in size. Clear? So this is the nature of the images formed by a concave mirror when the object is placed at infinite distance. Now what we'll do is we will try to gradually bring the object near to the mirror. The same concave mirror. Now we don't keep the object at infinite distance. We'll try to bring the object closer to the mirror, but we'll place it beyond C. Beyond C, C is what? Center of curvature. Clear? We'll place the object beyond C. It is not at infinite distance. It is at a finite distance which can be measured. So from this particular object, we'll consider a point on the object, and from that particular point on the object, we will draw two light rays, okay, to be incident on the spherical mirror, that is a concave mirror, whatever we are taking. So I'm taking two light rays like this. One light ray is passing parallel to the principal axis, another light ray is passing through the focus. So we have studied in the rules that after reflection, if the light ray which is passing parallel to the principal axis, the incident ray is parallel to the principal axis, the reflected ray will pass through the focus. If the incident light ray is passing through the focus, then what will happen? It will go parallel to the principal axis. That's what is happening now here. Now see where the two light rays which are reflected are intersecting. This is the point which corresponds to the point on the object from where the two light rays are emanated. Okay, so we'll get the image like this. Now the image is small in size. Image is formed between the center of curvature and the focus. So I can say the image distance. Now if you measure the object distance, I will measure from the pole towards the object. Okay, image distance is from the pole to the image. Focal length is from the pole towards the focus. And radius of curvature is from the pole towards the center of curvature. Now if you compare the distances, object distance is greater than radius of curvature, but image distance is less than that. But at the same time, the image distance is greater than the focal length. Clear? Now if you see, the image is inverted with respect to the object. Clear? And it is diminished. So the properties of the image here in this particular situation will be like the image position is between F and C. It is real, it is inverted, it is diminished. So at this particular position, if I am able to keep a screen, okay, I will be able to watch the image on the screen. If I don't keep the screen over there, we'll not be able to see the image. That's it. Because it is not caught on a screen. If you keep the screen at this particular position where the image is formed, we will be able to realize the image on the screen. Because it is possible to catch the image on the screen, it is a real image. It is an inverted image with respect to the object. And it is smaller in size, so we call it as diminished. Fine. Now you see the size of the object increased from highly diminished to diminished. When it was highly diminished, it was like a point sized image. Now the image is not a point size, it became extended. Okay. Now let us move the object further close towards the mirror. So we'll see what will happen. So we'll move the object closer and we'll place it at the position C. That means center of curvature. Now I'll again follow the same procedure. I will take one light ray parallel to the principal axis, another light ray passing through the focus. As we discussed earlier, this light ray after reflection will pass through the focus, and this light ray after reflection will go parallel to the principal axis. Let us see how they go. Now this is the position where the image is formed. So I'll get the image over here. Now you can see very clearly, okay, the size of the image is equal to the size of the object. Okay, very well clear actually. If I consider the two triangles like this, I will be able to very much clearly say, so this is one triangle. I can take this one triangle and this one triangle. I can compare the angles in the triangles and then find out, okay, that these two are equal in size. And where the image is formed, at the same position, center of curvature. Object is placed at center of curvature, image is also placed at the center of curvature. And one more thing is that the size of the image was increased compared to the previous case. Okay. Now earlier it was smaller in size compared to the object. Now the image size is equal to the size of the object. So now the characteristics will be like, okay, the object is placed at C, image is also placed at formed at C. Okay, object distance is equal to the image distance over here. It is real, inverted and equal in size. That is the nature of the image formed when an object was placed at the center of curvature position. Now let us move the object little bit further. Okay, what is happening? The object came closer now. It is lying somewhere between C and F. If that is the case, what is happening? The image size should increase actually. Does it increase? Let us see. As usual, we will take two light rays. I said the minimum of two light rays are important for me, or they are required for me to trace the position of the image. Clear? As usual, one light ray parallel to the principal axis, another light ray passing through the focus. The reflections are also as usual. After reflection, this light ray will pass through the focus and this light ray will go parallel to the principal axis. Okay. Now if you consider it this way. Now these two light rays are intersecting at this point. So we will have the image at this point. Clear? Now the image is formed at this point. It is magnified, bigger in size. It is still inverted. It is real. Why? How can I conclude that it is a real image? Because the two reflected light rays are intersecting, they are converging. So converging light rays will form real images. Diverging light rays will form virtual images. Simple. Clear. The difference between this case and the previous case is that everything is same, but the size of the image is increased. The position is that the image is moved away from the pole of the mirror. If you see, as the object is coming towards the mirror, the image is going away from the mirror. Okay. So this will be the nature of the images. Where is the object? Between C and F. But where is the image? Beyond C. Clear? Now it is magnified, bigger in size. Clear? Let us now move this particular object still closer to the mirror. Let us keep this at the focus. Now we'll take again two types of light rays. One will go like this, parallel to the principal axis. Another light ray, now I cannot pass it through the focus unlike the previous case. So what should I do? I should pass through the center of curvature. Okay. So I should draw a line from center of curvature to this particular point on the object. So it will go on straight and hit it this point. Then what will happen? Obviously, the angle of incidence is 0. So the angle of reflection is also 0. The light ray will retrace its path. The incident light ray, which was parallel to the principal axis, after reflection is passing through the focus. But the other one, which is passing through the center of curvature, is retracing its path. Now these two light rays are parallel. They are not convergent, they are not divergent. So somewhere the image is formed at infinity. Clear? So what is the nature of the image now? Because the image is formed at infinity is very, very highly magnified. Very much highly magnified. Clear? But it is still inverted. And if you place a screen at the infinite distance, you will be able to get the image on the screen. So still it is real, inverted and magnified. These are the 3 points. So whenever you talk about the nature of the image formed by a spherical mirror, okay, you will talk about two things. One, when you say nature, we'll talk about 3 things, not 2, 3 things. Whether it is real or inverted, real or virtual. Clear? Real is which can be caught on screen, virtual it is not caught on screen, that's simple. So based on that criteria, you will classify whether real image or virtual image. Second one, based on the criteria of size. Is the size of the image equal to size of the object or not? Is it less? If it is equal, okay. If it is not equal, is it less than that or is it greater than that? If it is less than that, you will say it is a diminished image. If it is greater than that, you will say it is magnified image. If it is neither of these two, it is equal. What is the point in it? Clear? If either it is diminished or it is magnified, that means it should be equal. There is no other alternative, right? Fine. And coming to the size of the image, magnified, diminished. Okay. So in real, inverted are not, highly magnified, equal in size or diminished. So these are the 3 points what we generally focus on when we talk about the nature of the images. With respect to position, when we talk about, we'll say yes. Where is the image position? Is it between, is it at F? Is it between F and C? Or is it beyond C? Or is it at infinity? So far, we have brought the object from infinity to the mirror and finally we have reached at the focus, principal focus. Fine. Now what will happen if we move the object still closer to the pole of the mirror? Okay. So fine. We'll bring it still closer to the pole of the mirror. What is happening? Let us see. Further again, we need to draw Ray diagrams only. Two rays we need to consider. So one light ray is passing again parallel to the principal axis. After reflection, where it will go? It will pass through the principal focus. That is clear for us. We'll see that. Second light ray, I am directing from the center of curvature. It is going like this, and then it is appearing to be. So when I am observing the image of this particular object in this direction, my eyes are over here. Okay. But these two light rays which are reflected from the mirror are appearing to diverge. When they are diverging, they cannot form the image on the screen. Simple. Clear. So you will have these two light rays which are produced back. Somewhere they are meeting over here. That means these two reflected light rays appear to diverge from this point. This is the point where I get the image. Now this image is peculiar, it is special. Why is it special? It is greater than the size of the object, fine. That is not the specialty of this object. Why? Because already we have seen magnified images were there. But this magnified image is formed beyond the mirror. It is formed by extending the reflected divergent rays. So the nature of this image will be like it is virtual image. No doubt it is bigger in size, so we will say it is magnified. Okay. And where is the image formed? Behind the mirror. Okay. It is formed behind the mirror. It is virtual, erect, and magnified. Clear. So these are the different possible positions of the object in front of a concave mirror, and correspondingly we will be able to get the positions of the images. Is this clear? Let us now summarize the points what we have discussed in the case of images formed by a concave mirror. Okay, so this is the table which gives you the information in a single shot. Better you note down this particular table. We are talking about object distance, second column image distance, third one nature of the image. First one, if you see first case, object is at infinity, so object distance is equal to infinity. Where is the image formed? At the principal focus, so image distance is equal to the focal length. Nature of the image is real, inverted, and highly diminished. If the object in distance is not at infinity but it is beyond c, okay, then image lies between f and c. It is real, inverted, and diminished, smaller in size. Next, if the object is placed at the center of curvature, then the image is also formed at the center of curvature. The image is real, inverted, and same size as that of the object. Okay. So correspondingly, we'll have the positions of the object. These are the images. You can see if the object is at infinity, how does the image form? If the object is beyond c, not at infinity, this is the shape of the image formed. At c, yes, equal in size. This is a ray diagram, corresponding ray diagram. Between c and f, this is a ray diagram. Now you can see here the image is magnified. Real, inverted, and magnified. When the object is at focus, image is formed at infinity distance. So the image is formed at infinity. So this is the case of the ray diagram. Okay. And if the object is between the pole and the principal focus, then we'll get the image beyond the mirror, behind the mirror basically. Okay. And it is a virtual image. So concave mirror can form virtual images, real images. It can also form highly diminished images, equal in size images, magnified images, highly magnified images. Clear? So this is the only mirror which can form like that, right? Let us now look at the nature of the images formed by a convex mirror. We have seen with concave mirror. Let us now see with the convex mirror. Now, if I consider a convex mirror like this, pole, center of curvature, principal axis, and the incident light rays when the object is placed at infinity. So, recall the rules what we have discussed in the previous class. In the case of a convex mirror, if the light rays are coming from infinite distance, the two parallel to the principal axis, okay, after reflection, they appear to diverge from the focus. They're going in all possible directions. If I retrace them back, I'll get it this way. Means what? The image is highly diminished. Where the object is placed at infinity, image is formed at the principal focus. Okay. Clear? So the nature will be like at F, that is a position. Okay. It is virtual, it is erect and highly diminished. Recall the nature of the image similar for the similar position of an object placed in front of a concave mirror. Almost the same thing, but except that, see, that almost the same in the sense it is highly diminished. But nature-wise, if you see, it is a real one, it is inverted one. But here in this case of a convex mirror, it is virtual, it is erect. Highly diminished is the same. Okay. Let us now bring the object from infinity towards the mirror, like what we have done in the case of a concave mirror also. So let us now bring the object is placed at this point over here. I am taking two light rays coming like this. So this is the one light ray. After reflection, it appears to diverge from the focus. One light ray directed towards the center is retracing its path. Where these two light rays are appearing to meet at this point. So this is the point where the image is formed. What is the nature? Very much simple, na? It is formed behind the mirror. So it is formed by divergent light rays. So it is a virtual one. Very clear on that part. Smaller in size compared to the size of the object. That is also clear. But one more point to be noted is that it is erect. One more similarity between the nature of the images formed in the convex mirrors and the plane mirrors is that in the case of convex mirrors and plane mirrors, both the cases, the images formed are laterally inverted. One difference is that in the case of a convex mirror, the size of the image is less than the size of the object. If it is a plane mirror, the size of the image is equal to the size of the object. That's the difference. Clear? So, the nature of the image here is that it is virtual, erect and diminished. Now, when I say it is diminished, when the object was placed at infinite distance also it was diminished. Now also it is diminished. Do you find any difference in these two diminished cases? Yes. When the object was placed at infinity, the image was highly diminished at the principal focus only. Now, when the object is approaching the mirror, image formed is also approaching the mirror. So, size of the image is also increasing. However, the size of the image can never ever be greater than the size of the object. This is a very, very important point. Clear? Let us see some uses of concave mirror. Where do we use generally this type of spherical mirrors? First, let us focus on the concave mirror. One is used in the torchlights or searchlights. You would have seen what is a torchlight, right? So there is a bulb at the principal focus, and behind that particular position of the bulb we have a concave mirror. So these torchlights and searchlights, they help in having a parallel beam of light. Clear? Second is like in shaving mirrors or makeup mirrors. So one thing peculiar in this particular case is that if we wanted to observe our face very much bigger in size, okay, when you look into a plane mirror, it does not appear bigger, right? Because the object size is equal to the image size, or image size is equal to the object size. If at all we wanted to look at a bigger image of ours, we need to take the help of a concave mirror. And how much distance should we maintain? We should maintain the distance between the face and the mirror, which is equal to less than the focal length. Then only we will be able to have a virtual magnified image. Okay, that case is used as an application in the shaving mirrors as well as the makeup kits. Not only this, even in the field of medicine also, the dentists use this way. They keep the concave mirror very close to the teeth so that they'll be able to observe the teeth, interior portions of the teeth, in a bigger magnified way. Clear? These are the advantages of concave mirrors. Let us now look at some of the uses of convex mirror also. So one thing is that OSRVM, I don't know whether you have anytime heard about this particular word, OSRVM. It is the acronym for outside rear view mirrors. Generally, these are the mirrors what we call them as OSRVM. This mirror we would have observed many times, but you don't know that it is called as an OSRVM. Might be the case. Okay. So these are the mirrors which are placed outside the vehicle so that the driver can observe the person coming from the back of them. Okay. It is easy for them because the field of view of the convex mirror is more than that of a plane mirror. Another example like this. You can see this itself is a OSRVM. One more mirror is also attached over here. Okay. So these are often referred to blind spot mirrors in a colloquial language. Okay. So that these will help to view the bottom portion of the vehicle in which the person is driving. Okay, in this particular bigger mirror, because the radius of curvature is very large and the focal length is very large, okay, they'll not have a much wider view as much they have in this particular smaller one. Okay, like this, you'll be able to see a large distances. Now if you observe closely on this type of mirrors, some text will be written over here like this. Okay, objects in the mirror are closer than they appear. The significance of this statement is that if you look into the convex mirror as an OSRVM, okay, what is happening? From the you will observe the person who is coming at the back. The image of the person will be appearing to be very small here. So thinking, because it is very small, you may think that the object is very far. That means the person is very far from you. He is not close by. But it is not the case. The object is still closer. He is closer than how much distance you are thinking. So it's a bit of caution. Okay, what is written over here? Why? Because if you are going in a vehicle and you see the person coming from the back, some on a bike, and you may think that okay, the person is coming from very far distance, there is no problem. Now I can take a sudden right turn, which is not at all advisable. Okay, you have to be very careful when you are taking a turns in this type of vehicles. Clear? Now let us see some more examples where these convex mirrors are helpful. In ATMs, as a security measure. Clear? At junctions. This is also as a security measure. Otherwise, what will happen? The steep road is there. At the corner of the steep road, this particular mirror is placed. So the person coming from one road will be observing in this particular mirror if any in the opposite direction any other person is coming or any other vehicle is coming in the opposite lane where he is not able to see directly. Okay. Clear? These are all the applications of the convex mirrors. Clear? Let us now list out some of the important points about the images found by spherical mirrors. Okay, better you note down these points. First one, only concave mirror forms real images. Real images are always inverted with respect to the object. Okay, with respect to the object, real images are always inverted. As an object approaches a concave mirror, the real image recedes the mirror but not proportionately. Not proportionately in the sense, if the object distance is decreasing by 5 centimeter, image distance will not increase by 5 centimeter alone. It may be greater than that. Clear? Next point. The image of the object placed at C of a concave mirror is equal in size to the reference object. Here you will say it is equal in size. Okay. Virtual images can be formed by all mirrors, that is plane mirror, concave and convex. Difference lies in the fact that in the case of a plane mirror, the image size is equal to the object size. I am talking about the virtual images only. In the case of a concave mirror, the size of the virtual image formed is greater than the size of the object. Whereas in the case of a convex mirror, the size of the virtual image formed is less than the size of the object. Clear? Next one. Plane mirrors always form a virtual image of the same size. Just now we discussed that point. As an object approaches the plane mirror, its image also approaches the mirror proportionately in the case of a plane mirror only. Next, virtual images are formed by concave mirrors are always magnified. This point also we discussed. Clear? Convex mirrors always form diminished virtual images. Clear? As an object approaches a convex mirror, its image also approaches the mirror but not proportionately. This also I told you. Clear? These are all the nature of the images found by spherical mirrors. Clear? Now let us look at one of the important aspect in reflection of light. That too regarding spherical mirrors. That's what we call Cartesian convention of spherical mirrors. What is this Cartesian sign convention? Okay. When I consider this particular image over here, I am taking the image of a concave mirror. Okay. This concave mirror, I have a pole over here, P. Then I am assuming this principal axis as x-axis. Okay. And I have an object on the left over here. So the light rays from the object will be incident on the mirror, so they travel towards the right. Okay. Then if the image is formed here in front of the mirror, it will be an inverted image. Okay. It is an inverted image over here, and this image is lying upside down because it is inverted. If at all the image is a virtual image for this particular object, it will be behind the mirror as shown by the blue line. Right? Now, to measure the object distance, image distance, focal length, radius of curvature, all these things, what we'll do, we will start from the pole. Listen, this very, very important. We will measure from the pole. All distances we will measure from the pole. If at all I wanted to measure the focal length, so my principal focus will be on the left side. So I will go from pole to the focus. Clear? So this is in the direction opposite to the direction of the incident light. So we'll consider it to be negative. Why? Because pole I am considering at the origin. So everything to the right of the origin will be considered as a positive. Left of the origin is negative. Okay. So another way to look at it is that the distances measured in the direction of the incident light are to be taken positive, and the distances measured in the direction opposite to that of the incident light are taken to be negative. Is it clear? I repeat again, distances measured in the direction of the incident light are to be taken positive. Distances measured in the direction opposite to the direction of the incident light are to be taken negative. First point, what was it? Pole. From the pole only we will measure all the distances. These 2 points, if you remember, we will be able to get all the sign conventions. Okay. Apart from these two, if we consider the height of the object or the height of the image, okay, which is positive, which is negative, above the principal axis, whatever the heights you measure, you will measure it as positive, and below the principal axis, that means in the downward direction from the principal axis, whatever the heights you measure, those heights you will consider to be negative. So that means here this particular image height will be considered negative, this particular image height will be considered positive. These are the points. So if you try to summarize all those points, first one is that all distances are measured from the pole. Second point, distances measured in the same direction of the incident ray are taken as positive, and distances measured in the direction opposite to the incident ray are taken as negative. No confusion at all. Clear? Next, third point, perpendicular distances, basically heights, above the principal axis are positive, and perpendicular distances below the principal axis are taken negative. So focal length, radius of curvature are negative for concave mirror and positive for convex mirror. As far as object distances are considered, object distance is considered negative for both convex as well as concave mirrors. Why? Because when you are measuring the object distances, you will go from the pole towards the object which is in the direction opposite to the direction of the incident light. Is it clear? So that is the reason object distances are always negative irrespective of whether it is a convex mirror or a concave mirror. Clear? Let us now look at one of the important derivation of the expression that is called as mirror formula. Whatever the sign conventions we have discussed, we will apply those sign conventions in this mirror formula to know the nature of the images formed and also the position of the images formed when an object is placed in front of either a concave mirror or a convex mirror. Clear? To derive the mirror formula, let me take an example of the image formed in a concave mirror. So AB is the object over here, P is the pole of the concave mirror, okay, F is the principal focus, C is the center of curvature, okay. So if you see the light rays are going straight like this, it is getting reflected over here passing through the focus. This light ray is parallel to the principal axis, so we know it. Another one passing through the center of curvature is retracing its path. The position where these two light rays are intersecting here, this point, that is a point where I will get the image. Apart from these two light rays, I will consider one more light ray which is directed towards the pole of the concave mirror. It is getting reflected and it will pass through the same point. Okay. Now, where will I get the object distance? P to B, that is the object distance. And what is the image distance? P to B dash is the image distance, because A dash B dash is the corresponding image to AB. Clear? Radius of curvature is PC. Focal length is PF. So with this information, we will try to derive what is the mirror formula. Okay. So here, this is the things what we have discussed right now. PF is equal to PC by 2, that is also known for us. Focal length is equal to half of the radius of curvature. Now we'll consider two triangles which are important. One is ABP and another is A dash B dash P. These two are similar. How do these two triangles appear to be similar? Let me show you. Okay. See, this is 90 degrees. Here, this is also 90 degrees. So, these two angles are equal in the two triangles. Okay. Next is this angle here is angle of incidence and this angle here is angle of reflection. These two angles are also equal. So, if these two angles of one triangle are equal to two angles of another triangle, so obviously the third angle of one triangle is equal to the third angle of the other triangle, then the two triangles are similar. So when the triangles are similar, we will get corresponding ratios of the sides to be equal. So we'll get A dash B dash divided by AB. A dash B dash is the size of the image. AB is the size of the object. That we'll get it as PB dash by PB. That is first point. Clear? Now we'll try to apply the sign conventions over here. So PB dash is equal to minus V and PB is equal to minus U, applying the sign conventions. So minus V by minus U is again same as V by U. So what I'm going to get? I'm going to get it as A dash B dash divided by AB. I'll get it as V by U. That is the second equation. Let me keep this equation aside. Now we'll try to take one more set of triangles. One more pair of triangles which are similar. That is what? ABC and A dash B dash C. How these two are similar? Let me show you. This is 90 degrees, very clear. This is also 90 degrees. Okay. Now this angle is equal to this angle. These two form vertically opposite angles. So obviously the third angle in this triangle will be equal to third angle in this particular triangle. Okay. So the two triangles are similar. If that is the case, I will have A dash B dash divided by AB. I'll get it as B dash C divided by BC. B dash C, I don't have the direct relationship. I need to write it in terms of P to B and P to C. Okay, so let me write that way. I'll get it as PC minus PB dash. That is what? B dash C. Similarly, BC I will get it as PB minus PC. What is PC? PC is nothing but R, radius of curvature. Okay, and PB is nothing but U. PB dash is nothing but B. I got these things. Once I get these things, what should I do? I should apply the sign convention. Simple. Just follow the steps whatever we are doing. Try to note down these things. Okay. So using the sign conventions. Try to recollect previously what we have done. We have taken one pair of triangles which are similar. That was A, B, P and A dash B dash P. Now we are taking A, B, C and A dash B dash C. In both the cases, we have taken the ratio A dash B dash divided by AB. So in the first case, I got this second equation. Okay, this one I got it. Now I am getting this fourth one after applying the sign conventions. What can I do now? The left hand side of the second equation and the fourth equation are equal. So I can very much conveniently equate on both the right hand sides of this particular expression. Okay. So once I equate these two, now remaining thing is only simplification. Just try to simplify it. Cross multiply V into minus U plus R. U into minus R plus V. Then you open the bracket, multiply it bring the u and v terms one side, remaining terms on the other sides. So uv and uv, I will have it on the left side, I'll get it as 2uv, whereas I will get on the right side as r into u plus v. If I divide both sides with like r, and here uv by u plus v is equal to 2 by r. If I divide, 2 by r is nothing but 1 by f, and I will have on the right side 1 by f is equal to, on the right side I will have 1 by u plus 1 by v. This is the fifth equation. It is this fifth equation which I try to take it as the mirror formula. Is this clear? So we know this because f is equal to r by 2, so 1 by f is equal to 2 by r. So as it mentioned, this will be the mirror formula for a concave mirror. Similarly, you can also proceed for a convex mirror. Now, as we have discussed in detail about the concave mirror, how to derive the expression for it, you make a try and try to derive the expression for similar expression for convex mirror. This is the figure what you can make a note of it. Okay, so I'll tell you what are the, I'll give you a clue. Okay, don't be worried that you are given a Herculean task. Okay, I'll give you a small clue as what are the triangles to be considered for deriving the relation. So A, B, C is one triangle. Similarly, A dash, B dash, C is one triangle. Clear? And similarly, another set of triangles, what are similar triangles, what we need to consider is A, B, P and A dash, B dash, P. These two triangles, if you consider, totally two pairs of triangles. Okay, I repeat again. First pair is ABC and A dash, B dash, C. Second pair is ABP and A dash, B dash, P. If these pair of triangles are considered, okay, then you will be able to derive the expression for the convex mirror. That is mirror formula in the case of a convex mirror. Clear? Now let us look at this important aspect. This is magnification in the case of a spherical mirror. You define it as the ratio of the image of the height to the height of the object. Because every time you are comparing the height of the image only with respect to the height of the object. Clear? So here if I consider M magnification, going by the definition, I can write the expression as height of the image divided by height of the object. If I write in short, HI divided by HO, or I can write it as A dash B dash divided by AB, refer to the images in the previous two derivations. Okay, so A dash B dash divided by AB, if you consider, that is nothing but V by U. What is V? Image distance, and U is object distance. Clear? So if you take that and if you apply, then in this particular expression, if you apply the sign convention, you will get it as minus V by U. Okay, why? Because irrespective of whether V is negative or positive, okay, U is always negative. So we'll get the relation magnification is equal to minus V divided by U. Okay, if you consider the height of the image, if it is a convex mirror, okay, this HI will be positive and HO also will be positive. If it is a real image which is inverted, then in the case of a concave mirror, then I'll get HI to be negative, HO being positive. Okay, so either I can apply these two, that means M is equal to HA by HO or M is equal to minus V by U. Any of these two expressions I can use to get the magnification. Sometimes given the problem, I need to relate these two so that I'll be able to get a relation between the height of the image, height of the object, and image distance and object distance. Clear? We'll now solve a simple problem to understand whatever we have derived so far. One particular question here, a rear view mirror of an automobile. Rear view mirror of an automobile. Why I am repeating, I'll tell you. Has a focal length of 2 meter. This is given, very important for us. Focal length of 2 meter. If it locates a person standing at 4 meter from it, find the nature, distance and magnification of the image. Okay. What is the mirror over here? It is a rear view mirror of an automobile. Why I am highlighting these points? Because we have seen that for an automobile, the rear view mirror will be made up of a convex mirror. In the case of a convex mirror, what would be the nature of the images formed? Nothing but virtual, erect, diminished. So I can write it as virtual, erect and diminished. Diminished is small in size, erect this is not upright down, and virtual it cannot be caught on screen. These are the nature of the images. Next, you want the distance of the image. How do I get the distance of the image? I need to apply the mirror formula. What is given? Focal length of 2 meter, f is given. So let me write f is equal to 2 meter. If it locates a person standing at 4 meter from it, that means object distance is equal to 4 meter. If I apply sign convention, this will be negative. If I apply sign convention also, focal length is not negative because it is a convex mirror. Okay. Now I need to know what is the image distance. V is equal to what? Okay. So I'll apply the formula 1 by f is equal to 1 by v plus 1 by u. Okay. I need what is v, so I'll get it as implies 1 by v is equal to 1 by f minus 1 by u. I'll simplify it. I'll get it as u minus f divided by uf. Okay. So when I take this way, u minus f by uf is 1 by v. But I want it is v, implies v is equal to uf divided by u minus f. Now I'll substitute. Okay. So what is u? Minus 4. So minus 4 into f. 2 divided by u is minus 4 and this is minus 2. So it is numerator is minus 8, denominator is minus 6. So if I cancel out the negative sign, I'll get it as 4 by 3 meter. That is the image distance. It is less than the object distance, please remember. Consider only the magnitude because it is 4 over here, it is 4 by 3 over here. Okay, then so we have found out the nature, we have found out the distance, magnification of the image. How do I get the magnification? M is equal to minus v divided by u. Okay, so minus what is v? I'll get it as 4 by 3 and what is u? Minus 4. So if I take this and simplify, I get it as 1 by 3. 1 by 3. What is the unit of magnification? Do you have units? No way. Clear. Why? It is a ratio of the distances. If you go by the definition also, height of the image divided by height of the object. Both are heights. I am taking the ratio of the heights. So no units at all. Magnification is just a number. That's it. Clear. So hope you are clear with the solution of this particular question. Right? Hope all the concepts are clear in this particular chapter. Let us just have a quick recap of what we have discussed in this particular class today. That is, we started off with the images formed by concave and convex mirrors. Okay, when the object is at infinity in front of a concave mirror, the image is highly diminished. Okay, it is inverted and real. If the distance is finite, we will have the image formed between the focal length and the center of curvature. I mean, distance between the focus, principal focus, and the center of curvature. Okay, and it is inverted and diminished. If the object is placed at center of curvature, image is also formed at the center of curvature. It is inverted, equal in size, and real. Clear? If the object is placed between the center of curvature and principal focus of a concave mirror, then the image is formed beyond the center of curvature, which is inverted, real, and here this time it is little bit magnified. Okay. If the object is placed at the principal focus in front of a concave mirror, then the image is highly magnified, inverted, and real. Clear? If at all the object is placed between the focus and the pole of the mirror, then the image will be virtual, magnified, and formed behind the concave mirror. Whereas in the case of a convex mirror, the nature of the images is almost the same. Okay, they are virtual, erect, and diminished. The difference is if the object is at very infinite distance, the image is formed at the principal focus highly diminished. For all the other distances, the image is formed between the pole and the focus. As the object approaches the mirror, the image also approaches the pole of the mirror. It is magnified as compared to the previous case, but the magnification can never be greater than 1 or can never be equal to 1 also. The images formed by convex mirrors are always virtual, erect, and diminished. Next, we derived the mirror formula also. That is 1 by f is equal to 1 by v plus 1 by u. We also have seen the Cartesian sign conventions, which states that all the distances are measured from the pole of the mirror. Object distances, image distances, focal lengths, and the radius of curvatures, all these distances measured in the direction of the incident light are taken to be positive, and that in the opposite direction are to be taken to be negative. Clear? We also finally discussed what is magnification, which is nothing but ratio of the size of the image to size of the object. Hope you have enjoyed the session. Okay, try the questions. Okay, whatever the questions are there given as the homework, you can go through the exercise part of it, this particular chapter, this particular section, reflection of light. Okay, you have test your basics questions, okay, and skill builder exercise questions also, which comprise of knowledge based, understanding based, and application based questions. I wish you a good luck in solving them. Once you are ready with it, be ready with the next session where we discuss the solutions of that particular part. Until then, have a good day. Thank you for watching.